Hello, good afternoon, everyone. Thanks for the introduction, Mr. Chairman, and I'd like to thank the organizers for inviting me. So I'll be talking to you a little bit about our experience on advanced mathematical modeling and how we understand it can really serve the needs for the cement industry and in the new challenge with the SCMs. So as mentioned, I'm a professor at the University of Rio de Janeiro in Brazil. And also, I'm here also as part of this GCC, Global Communication Collaborative. So if you want to chat to us, we're right in the beginning, in the entrance here of the venue with the booth. Well, if you look at how we model processes in this field, comminution and actually even cement in general, in the past, we relied on empirical information. We use manufacturer books and records. Of course, more recently, we have been using phenomenological models and very happy about them. We can do a lot of designs and improvements. And of course, steady state simulators where we actually put every unit operation in there. And it has served as well. Well, anyway, but we are in the digital revolution right now. So definitely we are more and more aware of the opportunities on site, which is mechanistic models, models that have the details of how the process actually operates. Well, of course, we're talking about digital twins. We want to be able to see in the plant a simulator that actually in real time can replicate what's happening in the plant and can anticipate things that we can do in the process. Of course, Industry 4.0 is all around us as far as being able to use all online information and understanding to be able to make decisions, better decisions. And of course, if you look at process industries like the cement, we're talking about really how to be able to cope with the variability in the process, the fluctuations. So steady state simulators are no longer able to deal with that, and so we have to rely on dynamic simulators. So to be able to talk a little bit about this and how we are engaged with some of these challenges, we are working on a number of technologies. Today, I'll really focus on technologies such as the discrete element method, and in this case, just illustrated with the smooth particle hydrodynamics, just to show you a small tumbling mill without particles, just with fluid and media, that the ability that we already have to replicate this, and we're already using commercial software. This is done really by my students using commercial software in the lab. So these are all technologies that have evolved quite a bit in the last few decades, and we're happy that we are having a leading role on that. Well, on the other hand, we're talking about cement, and we already heard plenty about this morning on the opportunities and challenges of cement 2050, the neutral carbon, and so on. So there's definitely a lot of need in this industry to reduce the carbon footprint, reduce the energy demand, and that, of course, goes into improving cement efficiency in production in one hand, and the other hand, using, of course, less and less clinker. And when we look at these two opportunities, obviously SCMs and admixtures appear both as fillers without really hydraulic capacity, but also SCMs. And when we talk about the number of materials, of course, plenty of them, we have plenty of experience like blast furnace slag, fly ash. But for instance, in Brazil, we have been working, of course, calcine clays, a lot of biomass ashes, and even concrete recycling fines and so on. So we need to be able to see how we can better cope with these materials and understand the challenges that they have and what we can do in grinding to actually improve upon them. Well, of course, we know plenty that there's a lot of different things that can be done to improve the quality of SCMs. But we do understand that, of course, comminution is right there in the center. There's a whole lot of work that we have been doing in the last couple of 15 years or so, that we really have understood that a lot of problems that we have with some SCMs, for instance, a lot of carbon can be dealt with finer grinding, more controlled grinding, instead of really reburning, which is quite a challenge. So we understand that there's a lot of scope in comminution that can be used to actually improve and to make sure that these SCMs, even though they are really quite variable sometimes, they can be really controlled through grinding. Well, but what can we do different from what we did in the past? It's just really buy a mill and operate it. Well, we understand that we can make the most out of the two worlds, which is the challenge for the new SCMs in the future, variable materials, with also the abilities that we have right now to deal with information, to deal with understanding of this unit operation, which is grinding. So a lot of the advanced mathematical models have evolved a lot in the last couple of decades, not much through the cement industry, but mostly through the mining industry, which is a neighbor of the cement industry. So a lot of that can be really very easily pulled into this field and create a lot of value. And we understand that even today, later in the afternoon, you'll be seeing, and tomorrow, presentations on novel grinding technologies. And there's plenty of those being analyzed and being presented. So how can we really find the best way to really develop a new technology and test a new technology? We understand that better understanding of the process, better models will put us in a way that we can really search for new technologies and really even do virtual prototyping. So, and of course, develop materials, SCM, through optimization that goes from the lab, but also understanding how this information can pull very efficiently to a large scale, which is really a challenge to go from bench to a large scale in this industry. So this takes us to the challenge of how can we really develop and improve this advanced understanding in the field of comminution. So basically, in order to do anything in this new scenario of understanding of how comminution can be better described, you need to understand the most basic thing, which is a cement clinker breakage event inside a mill or any particle inside a mill. So you need to understand how actually particles break. And different approaches have been used really by our group and other groups on how to simulate this simple event, which is crushing of a single particle inside a mill, just a grinding ball hitting. And in this case, we actually identified many years ago, you have to take two paths. One path is what I called explicit. So you have to really put particles inside your simulation and really crush them. And there's the other approach, which is I called implicit, which is the way that we actually put particles implicitly in the simulation. We don't put them exactly appearing, but they are being accounted for using the proper models. I'll be showing you today examples of the two that we have been developing the last couple of decades. So for instance, the first case, that how can we actually describe particles explicitly in a simulation to be able to see really comminution happening? This is what we call embedded in DEM. A number of people really have worked on that. Over 25 years ago, people already were proposing how we can actually couple these technologies and simulate in large scale. But really a technology that really has evolved to be able to simulate larger scale systems is really what we call particle replacement, which is really to break a particle and instantaneously replace by its fragments. It's just illustrated here in the upper right, the down right. One particular case for polyhedral particle, and that's exactly the one that we chose to move forward because we want to be able to simulate larger systems like we have in industry. So really these so-called particle replacement models really are exactly like that. Every time a particle is crushed, it is instantaneously replaced by fragments. So you see in a simulation the particle being replaced by its fragments. The key thing is that they need a realistic condition for fracture. You need to see that now that particle should no longer exist because only fragments, and you need to have a credible size distribution coming out of that. And this is really good for non-media mills, for instance, like a crusher and other type of mills. Well, the other way to look at modeling is when you look exactly like a mill, a tumbling mill like that. Of course, it can be an industrial mill. So in this case, the population of particle is enormous. So in this graph, for instance, I just considered the case that you have a mill more or less of 30 centimeters in length, which is just a slice of a mill. In the case of a small lab mill, could be something like this, 30 centimeters in diameter. In this case, you have no more than a few hundred particles in a simulator. That's not a big issue. The problem is that even with a small slice, if you increase the diameter of the mill, if you only put the media, you're still less than 1 million particles, which you can simulate with no problem, just a few hours. The problem now is that if you include particles in this simulation, it can go very easily to the billions of particles. So unfortunately, even though computers are quite powerful, it's not going to be in my lifetime that I'll be able to see simulations with billions and billions of particles. So what do? Then in this case, we only simulate with the grinding media. Now we have to be smart enough to get this information and put into a proper model to predict the process. And the way that we do this is using these pieces of the puzzle, which is on the top left is actually the DEM simulation that you just saw, the grinding media moving. On the bottom left is what I'll talk about, is the model that I developed back in my PhD to describe breakage. But right in the center is exactly the last piece of the puzzle, which is how much material is being nipped every time balls collide. And this is important because it depends on a number of things, on the grinding media size, depends on the fluidity of the material, and that's important because that's where grinding heads really do most of their jobs, is really to make sure that you have just a monolayer of particles. And on the right, it exactly is where we develop the new solutions, which is what we call microscale population balance model, which is essentially being able to get all this microscale information into a scale that we can use information, which is predict the size distribution. As I mentioned here, this is really ideally suited for any type of media mills, and it can really be used, deployed to very large scale mills, industrial scale. So what really the model, in the end of the day, will be able to do is exactly that. For every single nip inside the mill, every single collision, it will be able to say how much material is nipped, and of that material that is nipped, how much will actually be broken, how much the material will not be broken but will become weaker, and all of this is being taken care of in this so-called microscale population balance model. So this information has already been put together, and all we need is to really understand what is happening inside that mill and how the material characteristics will affect all of these. So some materials are more amenable to surface breakage, some are to body breakage, and all of these will be able to capture. Well, so the key thing is that now we need a proper breakage description of how clinker breaks, how this particular SCM breaks. So really, the key thing is that we have to feed a lot of information on how particles do respond to breakage. And I think I stressed there that we are accustomed to Hargrove grindability numbers, work index. Those are all fine for a high-level type of description of how much resistance. But if you want to understand the detail, we need to open this black box, which is exactly what we did, is to understand how particles respond to surface breakage, how particles respond to body breakage, they shatter. So all of this was basically what I did about 25 years ago, last century, I'd say, in my PhD, when I did in the US. And back then, essentially, I opened this black box to understand how can we describe every single aspect of particle breakage, initially on a single particle, but of course, the whole idea here is to be able to carry this information to the full equipment. And so just to illustrate in the upper left, we know that even if you're very careful producing materials, build materials, they're never constant. They're always variable. So you need to describe the variability in size, in strength, exactly the upper left. And even if you do really have a material that is fairly uniform, and you can see here that there is still a variability in terms of particle size. When you feed particle sizes of different size, they really do have different strengths. Finer particles are tougher. This is all taken care of in the model. In the middle upper one, there's the fact that you weaken particles when you hit them over and over again, and eventually they'll break. You have to account for this amenability. And in the lower middle here, there's the effect of losing slowly material from the surface, and we account for that as well. And in the right there is that T10, is that the intensity of breakage in each event. All of these are actually pretty much the pieces of the puzzle to say what happens in that every single impact event that happened in your mill. So with all these parameters characterized, all these understood, we can definitely go now either to embedded simulation or implicit simulation to be able to characterize material. Just to illustrate one case here, we have done a lot of work with different ores and different materials, but just to illustrate one particular case that we played around with this concept, which is, some of you are aware of one of the SCMs, which is sugarcane bagasse ash, which is really very cellular material like this. It is usually very contaminated with quartz because of harvesting. And this quartz obviously is much tougher. You can see, for instance, looking at single particles there, the sugarcane bagasse ash is much weaker than the quartz, so you can really characterize that. We could very patiently break particles one by one, and this type of information feeds our ability to simulate this material inside the mill. We have done exactly that and demonstrate that we can differentially break these two materials and concentrate the sugar cane. So really just to use the rest of my time, I'd like to just show some examples on how we have deployed this approach to simulate different systems. As I believe some of them of interest here for the audience in the cement business. The HPGR, the ball mill, the stirred mill, and the inertial classifier, which is not a mill, but I think it's another approach to model that we have used. Well, of course, the HPGR, quite used in the cement industry, replaced a lot of ball mills many years ago. And here, for those of you who are not very familiar, essentially are those two counter-rotating rows, with the difference that one of the rows is floating, which is pressurized by pistons in a hydraulic system. And essentially, what you have is application of energy and quite a substantial size reduction. And that's on the right, one example of these HPGRs operating in industry. Well, we wanted to be able to simulate this. This is really from 10 years ago, but really I like because the colors are changing, because this really changing color means that that row is actually moving. So we are able to predict what happens exactly during this application of forces that really results in that row moving, which is exactly what happens in practice. Well, since then we have done really very big simulations, and we have been able to show something that we already knew, which is very close to the bottom here, 0 position, or 0, 1 position. That's where we have really the higher stresses, higher forces, whereas fairly much higher, like 4 or 5, the pressures are extremely low on the bed, so you can really go and look inside the machine and understand how the effect of many variables will be on the profile. But more than that, I think every time we look at a machine, we think of a machine when it's brand new, which is fine. And we buy it brand new, the rows are brand new, but very soon, after some time, it will wear. And the important thing is how it will respond when it's partially worn. And just to illustrate here, the red and the blue show two types of patterns, of course, very exaggerated for you to see, but it's really very small, just a couple of millimeters wear here of these two row conditions, just to show that one is more trapezoidal on the top and the bottom is more parabolic. And you can see, for instance, what the effect is on the profile. When it's brand new, it's very nice profile, just drops forces on the edges. But as soon as you have wear, only 2 millimeters wear, you see that the forces completely change. So you get really, whereas in the beginning you get finer material in the middle, now you get finer material close to the edges. So it is important to be able to understand this, and simulation has allowed us to exactly measure that. Of course, we have validated a lot of this for iron ore. And now the other question that many people have is that, well, originally these machines have cheek plates, which is just contention side plates. Well, a lot of machines today are being replaced with these side flanges, which in this case were smooth, or this case were actually with studs. And we were wondering, what would be the effect of this? We had already results from plant scale and full scale, and just to show how the material flows. In this particular case, the original one, the material flows relatively nicely here, and then escapes a little bit from the edges. And then when we simulate the smooth flanges, very much the same behavior. So the smooth flanges were not doing a whole lot if you don't nip the material. And then when you actually put the studded flanges, that's exactly where the difference appeared. So this is some of the things that we can do in simulation, is respond what-if scenarios and understand the effect, and of course, eventually validate it. This is pretty much the effect on the same changes on the force profile. You can see really quite a lot of improvement you get from the flanges, as you can see on the yellow, much more uniform, so showing the benefit that we know of flanges compared to cheek plates. So, but of course, looking at animations and pictures is all nice, but as engineers, we like to see numbers. and the numbers we could really verify, which is, for instance, we could see definitely an increase in throughput compared to the base case, but increasing power as well. So we have seen a number of companies who have retrofitted their machines and got increase in throughput. That's fantastic. But they have to be aware that they will need to draw more power. So they have to have a big motor there with some spare capacity. So just to show that we have done a lot of other simulations, a lot of different machines, like you can see here, a gyratory crusher, an eccentric roll crusher. And this is with companies make big decisions, because the key thing is that sometimes the scale of the tests that we need to do in reality are so large, is that you start to believe as much in simulation, because you cannot really rely on full testing to make decisions like this, primary crusher. Just really now moving quickly to the others, just for you to appreciate that we have been using our approach in other cases. Of course, the ball mill has been used forever in the mining and the cement industry. And what we have done, as I mentioned before, since we cannot put particles inside the ball mill to simulate realistically, we use the DEM coupled with the population balance, which we have developed. So just for you to have an appreciation of the type of things that we have been able to demonstrate. Of course, the same way that you have a small mill like this, you can have a large mill. But just to show a very well-known effect, which is what happens if you replace large balls with small balls in your mill, the same amount. What is quite obvious, you can see here, what we can see is small grinding media. It has really much higher frequency of collision events, whereas larger grinding media, much smaller events. But on the other hand, there's a trade-off, because the amount of energy involved in the collision increases as increase the ball size. And the beauty is that our approach actually can predict how fast breakage will happen in that mill, which is, if you use large balls, 40 millimeters, for instance, you get really good breakage of the coarse material. So it's nice to put in those old-fashioned cement clinker mills in the first compartment. But if you insist on using these large balls in the second compartment, the rates are so small, and pretty much we predict these results here. If you're not so obvious, what is the effect of mill filling? We know that, of course, you can fill the mill as much as you can, but as you reach 50%, you actually start dropping your power, because it's no longer attractive. Of course, depending on your mill, you'll be in trouble with that. Our predictions show exactly that. Very low fillings, not attractive. Very high fillings, no longer attractive. As you can see here, something in 20 or 30 were in the optimal range. So these are all predictions in the model, no empiricism involved whatsoever. Well, unfortunately, our cement partner didn't allow us to show their example, so I'll have to go to the mining industry to show pretty much the same type of thing, which is large-scale mill in closed circuit with classifiers. So we're able to predict what happens in this circuit, closed circuit, basically. And what we have done here in our simulator, exactly using that approach, we simulated this full mill, and we have been able to predict exactly the throughput, how much material comes back to the mill, and more importantly than that, we have been able to predict the product size distribution, the fine product, how fine it was, besides the circulating load. So these are all published results and demonstrate that we have been going the right direction. Of course, there are other types of mills which are getting a lot of attention in this industry. One case is the stirred mill, and the stirred mill, of course, in the minerals industry is really popular today. And of course, the booster mill here in the cement industry has gained popularity the last few years. And we have really done some work in the vertical-oriented mill, as you can see here. And you actually, just skipping this one, the same type of thing I shown before, we can do here, but now with frequency. So what is the effect of changing frequency, a tip speed? Anywhere from 1 to 2 to 2.5, very clearly show that the rates of breakage increase. There's a benefit to that. Of course, the wear will increase quite dramatically, but you really grind much finer. You can see there, what actually happens that as you increase the speed, the tip speed, actually what happens that the collision frequency is actually increasing. Amazingly, not increasing the collision energy. You're not changing a whole lot the energy, but the frequency of collision events. But if you want to see what type of ball size should I use, the same trade-off I showed before, which is if you use coarser balls like the gray line, it actually you get coarser particles finer, but you will have trouble grinding them finer than a given size. Exactly the opposite if you use smaller balls, and you can predict in this. So these are all things that are evolving. The same thing that I mentioned before. Very nice to do simulations with a machine brand new, but very often it is worn. What happens when it starts to wear? Like this screw, for instance, or the pins. It starts to wear very typically in the bottom. When you do that, just those simulations, they don't appear a whole lot, of course, quite dramatic wear here appearing. What we have seen is that what if you actually use different scenarios? As they wear, if you put more balls. As they wear, you actually put even more balls to keep the same power. All things that we have seen people do in plants, we wanted to see how they really respond here. And we confirmed what they have seen, which is when it's new, it actually does the best job. After that, you can compensate. Of course, the worst thing is to do nothing. If you do nothing, it goes to the red line. But if you compensate by increasing the amount of balls, you compensate partially. But you never get exactly the same throughput as you get before or the same fineness. So all things, the obvious things that come out of this is, what else can I do? Exactly, that's what this tool can help you identify without having to go to trouble in the plant. Just really the last one, just to show very wildly, we can play around with geometry here, the different diameter. And obviously here, what again appears that the optimal condition right now is exactly the one that was designed. Everything else, you lose a lot of power because a lot of dead zones will appear. This is really, I'd say, a very good evidence on how this can be used to improve designs. Just really another example here, but just to finalize, to go from grinding to classification very quickly, this is one classifier that has been becoming more and more popular in the industry. This is called inertial classifier, just a scheme on the right. And we are actually interested in describing, can we do a good job predicting what happens in this machine? We have a plant close to Rio in Brazil, and we have done a lot of testing. It is a commercial plant, so we have convinced the department to put some holes in there to measure pressure and velocity. And doing that, we could validate the description on pressure drop with and without material sand being fed. And we have done simulations to be exactly able to predict what happens in the material when it comes, how much material actually is being cut by this, and what is the pressure there. But of course, the important thing is to be able to, you can see here now the velocities and simulation in more detail, but the important thing is to be able to see what is the partition curve. The blue is the one predicted by the simulation, which is better than reality, but on the other hand, the real is the orange one. It's not yet spot on, but it's exactly pretty much in the same D50 value. So the beauty here is that we can play around with the machine virtually without having to really change because they only have one of these installed. So that's one of the potentials of these. Well, just really concluding, I think important developments in these advanced models have really been made in recent years. I have to say that mostly we're in the mining industry, but there's no reason why they shouldn't be taken up in the cement industry, considering all the challenges and opportunities. I think the development of a virtual mill or a virtual classifier, I definitely see it within reach. These technologies modeling are evolving very quickly. And I guess combining this digitization in novel developments, they definitely can help meeting the challenges of the cement and SCM of the future. So I'd like to thank, of course, a lot of the companies that are partners, but thank you.
Thank you very much. We are completely out of time, but I can allow one very quick question. Is there a quick question? Thank you. I'll take a chair's prerogative and ask a very quick question. Mm-hmm. How do you validate the CFD DPM model?
How validate the CFD DPM model? Well, so the CFD DPM model was actually pretty much a survey that was done, analyzing the feed and the products for the size distribution. But we actually validated as far as measuring the pressures and the velocities in 6 different points that I showed there. So it was not easy to convince the client to, with his new toy, to poke holes But he allowed us, and we got really good results for that. But basically, the pressure and the velocities were used to calibrate the model, and then the partition curve was the output.
Excellent. Thank you very much. Let's thank Professor Tavares again.
Okay.